Our talk today is by Curt Covey from Lawrence Livermore National Labs. He is an atmospheric scientist in the Program for Climate Model Diagnosis and Intercomparison. He's been at Lawrence Livermore for 28 years. He received his PhD before that from UCLA in geophysics and space physics. And an interesting fact about Curt is that he was a lead author on the reports of the Intergovernmental Panel on Climate Change, which won the 2007 Nobel Peace Prize along with former Vice President Al Gore. So we have a very celebrated and honored person in our midst today. And today Curt will give us a talk about atmospheric tides and the diurnal cycle on Earth and other terrestrial planets. Thank you, Curt, and welcome.
Thank you. I think I'm wired. And I'm certainly happy to be here. I've not been to the SETI Institute before, but I've been to this neighborhood many, many times going back to the Pioneer Venus mission in the late 70s. So it's always nice to be here. So my talk is on atmospheric tides and also the diurnal cycle in general. Almost all of my talk is going to be about Earth. And so I've put other planets in parentheses. I realized as I was putting together the talk that I don't really know that much about atmospheric tides on other planets, although I will mention them in passing. And I can see at least a couple of people in the audience who know more than I do about atmospheric tides on Mars, for instance. So as Cynthia says, I've been working at the PCMDI. Oh, and I forgot the M. Okay, so it's the program, PCMDI stands for Program for Climate Model Diagnosis and Intercomparison. So we deal with these climate models that are used to predict, as far as we're able, the future of the climate. And the job of the PCMDI, which is a little slice of the Livermore lab, the PCMDI's job is to study how these models behave and also to maintain a database of climate model output, which I'll be mentioning to you. It's available to basically anybody who's curious. So the talk's going to be mostly about atmospheric tides. That's a subject that I've worked on off and on throughout my research career. And in the last few years have got back to it together with some other people that I'll be mentioning. And I'm really in the middle of some calculations right now. So in a sense, I'm going to leave you hanging at the end because I don't have final conclusions. But I'll tell you what the background is, tell you what I've been doing on the tides. Tides are, atmospheric tides are, as opposed to ocean tides, are a rather obscure subject, and I want to put that in a broader context. So I'd like to say a few words right now about the context of basically the relationship between weather and climate. The tides in the atmosphere, just like the tides in the ocean, happen on a time scale of 12, 24 hours, and so they are very, very high frequency phenomena from the standpoint of those of us who study long-term climate change like global warming. They are therefore a piece of the connection between climate and weather. One of the things that people who don't work directly with the climate models often don't realize is that climate models nowadays are essentially the same thing as numerical weather prediction models. The numerical weather prediction models have been around for decades, and they're used by the weather services here and in other countries to make short-term weather predictions. So they don't always get it right, but of course, people are interested in making them better, and people have demonstrated that they do get steadily better as the compute power allows more detail and as people refine the concepts behind these models. But when we use them to predict long-term climate change, we're really using them for a totally different purpose, and this brings up a lot of confusion It's honest confusion on the part of people who are new to the business. Sometimes it's malicious confusion because, of course, people get this whole thing about climate change gets tied up in economics and politics, and it's often I've heard people ask me, well, how can you expect these climate models to tell you what's going to happen in decades from now when they can't even get the weather predictions right, all on a scale of a couple of days? And in fact, it is literally true to say that the climate models are out there trying to predict the weather. For instance, if you go to the database that PCMDI maintains, you can pull down a prediction of whether or not it's going to be raining in Northern California, say on the 1st of March of the year 2055. I mean, I can tell you where to find that prediction, but of course nobody believes that because weather is a chaotic system, and beyond a couple of weeks, it's just not possible to make detailed predictions. So it is true to make this rather hostile sounding statement, well, these models you use, they're trying to predict the weather, but nobody believes their weather predictions. What we do believe more than the weather predictions is the long-term statistics of the weather, averages and things. And so this statement is, while it's literally true, it can be very misleading, and this leads to all kinds of comments, and you really get these things from both sides of the political spectrum. If there's a big heat wave, there'll be one group of people saying, aha, this proves that global warming is worse than we thought, we got to do something right away about it, we have to follow my plan. And then if there's a turn toward colder weather, there'll be an entirely different group of people come out and say, well, aha, this proves that the models are totally wrong, we shouldn't believe them, it's not a problem. Nevertheless, this whole consideration is something that should not be dismissed. It's common for people in my business to say, well, you know, when we get these comments, the quick answer is, well, the climate and weather are two different things, don't confuse them. But I think that's not really sufficient, because another old saying that's perhaps a little bit hostile is the saying that climate is what you expect and weather is what you get. And that's unfair to the models, and the models really do things right. But weather is what you get. And so we have to make this connection between what the models are telling us, you know, what are the models telling us is going to happen. For instance, their indication, the models are telling us, well, in a warmer world, we're likelier to have drought in the western United States. Okay, well, we believe that. Then how does that reflect back on what's actually going to happen in Northern California? So that whole connection between weather and climate, I think, is one of those grand challenges that we do have to face. So it's not sufficient to just say, well, they're two different things. So the main part of my talk basically has the theme of, as I've said, high time frequency climate data. And well, both the data, the observations and the model output provide basically a bridge between the climate and the weather. They can help us make that connection, and in a very small way, I think the tides are a part of that connection. I will mention in particular the database that my group maintains. This is CMIP, which stands for Climate Model Intercomparison Project. And in particular, there's a subset of the CMIP climate model output that gives you 3-hourly snapshot every 3 hours of what's going on. It's a huge amount of data, but it is there. That's where you can pull down this prediction that nobody believes about whether or not we're going to be raining 50 years from now. I also want to point out that there is a corresponding observational database that's coming into place alongside the CMIP database at basically the same website. This is called OBS for MIPS, Observations for Model Intercomparison Projects. And this is a very exciting project, just got started a few years ago. It's a collaborative effort between our group and a couple of NASA Earth Science places, notably people at JPL and at Goddard. And so we're basically putting onto our model output, alongside our model output, we're getting satellite observations to compare it with, formatted in the same way so you can process them conveniently with the same computer scripts. So I do want to highlight OBS for MIPS, and I'll be showing you a little bit of that. Okay, so finally, the atmospheric tides. I'll be talking about them in some detail, including some algebra, so brace yourselves. There is a classical linear wave theory that was developed by Dick Lindzen and others many years ago, and I'll be talking about comparing that with simulations from the modern climate models. Do they give you the right answer? They do give you the right answer, but perhaps for the wrong reasons. And so Dick Lindzen, if you know him, he likes to identify model flaws. And so he got very interested that in this case, perhaps the models are getting the right answer regarding the tides for sometimes the wrong reasons. And I'll finally finish up with another example of this high-frequency database. This is a new project that we're just starting to work on about precipitation. And it's certainly of great current interest. And I've been basically looking at the diurnal cycle of precipitation. In a sense, this is the next logical thing to do, but I don't want to take credit for that because it was really kind of opportunism on my part. I realized one day that the scripts I was using, the little computer programs I was using to diagnose the data for the tides could just work just as well for the precipitation. So it was kind of an act of opportunism. Okay, so now comes crunch time. I have to figure out how to change the slides. There we go. Okay, so let me say one more thing about weather versus climate, just to give a definite example. Talking about the current California drought. Here's a weather satellite picture. You can't read this, but I can if I step closely enough. Okay, this is February the 8th of this year. It's the last time, at least in the East Bay, that we got a whole day's worth of rainfall. And there are these beautiful satellite pictures you can get from this website. That's my favorite for the satellite pictures. So here we have a classic rain system, kind of looks like a hook. I guess this is the whole west coast from Vancouver down to Baja. And this was taken right as we were getting rained on. And I remember I looked at this picture and I said, oh, this is great because there's another storm right behind it. But as it happened, a ridge of high pressure built up, as it has done very often in the past few years, and blocked this and sort of steered the storm track to the north of us. So that's weather. It's all this nonlinear fluid dynamics. Certainly the ridge formation is nonlinear fluid dynamics. Difficult for models to predict. And to get to the climate, well, first of all, you take a time average. So here's the time average, year by year, California precipitation going back to 1895 when good records started. And even if you do it year by year, you get these blue points, which is just like all over the place. A lot of random stuff going on here, obviously. You can see, by the way, that the last few years, although very lower than the long-term mean, they still have not come close to breaking the record for 1977, which was the absolute lowest year. But then right after 1977, 1978 popped right back up there, and then a few years later we got the highest ever, which is I think 1982 or something like that. So even averaging over a year still has a lot of randomness in it. If you do a running mean over several years, you get this red line, and there you can see that this drought really does start to look unprecedented. This line, it still bounces around, but it's never been this slow before. So maybe this is unusual. Maybe this has something to do with the global warming in general. And I'll just refer you to a paper by a couple of my colleagues at Livermore that makes the case that this is at least partly due to global warming. So that is just meant as an example of the challenge of connecting climate and weather. And next point I want to make is about the database that we're maintaining. And I want to show you that we've got a lot of data out there at the 3-hourly time frequency. So Climate Model Intercomparison Project, there's a website, which I hope you can see. That's where you start if you want to pull down the data. And there's 23 different output fields that we have at this high time frequency. Precipitation is up there. And there is an AGU poster by one of my co-authors on that from last year, I guess. Other than that, I've not seen anything done with the precipitation data set. David Caroli and some other people have looked at the near surface air temperature at this high time frequency, and they published a couple of papers. But by and large, this data set has not been looked at, and I really want to encourage people to go into it. It is a lot of data volume, obviously, at 3-hourly frequency, but you know, this is the 21st century. You can probably deal with it. I have been looking at the surface air pressure for some time, and I published a couple of papers with Dick Linzen and some other colleagues on this, and that is really where we get into the atmospheric tides. So now I'm going to kind of shift gears and go deep into the subject of atmospheric tides in particular. So, atmospheric tides, it's something that I've worked on for decades, and it started way, way before my time. It actually started about 200 years ago. People started making the observation that in the tropics, at least, there was a regular twice-a-day peak in air pressure at the surface. You just take a barometer and run a time series, you're going to see a twice-a-day peak. Now the barometer, I guess I'm the one person in the room can read these things, so I'll just read them to you. This is from a classic book, which is published by Chapman and Linzen in 1970. So first point is that we really are dealing with a tide here in the same sense that we think of ocean tides as a piling up of water. When you take the surface pressure with a barometer, in effect, you're measuring the mass of the weight of the air, the mass of the air over your head. And so if the barometer is peaking twice a day, that means that you have a concentration of atmospheric mass passing over your head twice a day. So that kind of looks like the ocean tides. But a key point here is that these tides in the atmosphere are forced thermally, not gravitationally. Now we know, of course, that the ocean tides are forced gravitationally by the varying gravitational fields of the moon and the sun. The moon at least as much as the sun. But when you do the timing of the atmospheric tides, which of course you can do very easily if you have a long enough time series, you just get the period of the oscillations very, very accurately. What you find out is that the period of oscillations, the oscillations happening twice a day, but they're happening, the period is half of a solar day, not half of a lunar day. So the atmospheric oscillations always take place at the same local time worldwide. They're around 10 a.m., 10 p.m. local time. That's a fundamental difference from the gravitational tides. And so if the atmospheric tides were gravitational, you'd expect them to follow a lunar day, and they just don't. They follow a solar day. So if the moon's not affecting them nearly as much as the sun, then it's a thermal effect, not a gravitational effect. So gravitational tides in the atmosphere are thermally forced. They're not gravitationally forced. The same is probably true for Venus to the extent that we have observations. Some people will tell you we have lots of observations. I'm a little doubtful about that for Venus, but probably there's more than I know about now with Venus Express. And definitely for Mars, this goes way back to the old Viking landers. They observed very strong atmospheric tides right off the bat. They're actually much stronger much more noticeable on Mars than they are on Earth. For Titan, they're mainly gravitational, and there's a reference to that if you're curious on following that up. Okay, so this graph just shows you a daily series of atmospheric surface pressure. This is November 5th, 1919. Like I say, it's been observed for a long time. This is sort of classic observation. So November 5th, November 6th, November 7th, November 8th. So these are days. And in the tropics, Batavia used to be the name for Jakarta, Indonesia, when the Dutch were in charge. And so you can see very clearly a twice-a-day signal. It's very obvious in the tropics. Its amplitude, by the way, is about plus or minus 150 pascals. And it's a very, very regular oscillation. In fact, the little thing I underlined down there goes back to the days of the famous explorer Alexander von Humboldt 200 or more years ago. He said you could practically set your clock by it. It's 10 a.m., 10 p.m. maximum in surface pressure. So where does this come from? Why is this happening? Here's a diagram from my PhD advisor, Jerry Schubert, in a book published on Venus. So this is supposedly showing you atmospheric tides on Venus. In fact, you see if you're staring down at the north, this planet is spinning backwards, which Venus does, retrograde compared to the normal direction. But basic concept for Venus or Earth is that you're facing, the sun is out there somewhere heating up the part of the atmosphere that's directly below the sun. And there's some time lag, so the atmosphere is warmest a little bit past noon, and that will naturally tend to push the air to either side, and so you get most of the atmospheric mass happening a little before noon or 12 hours later. But wait a minute, why is it 12 hours later? Why are we getting this twice daily maximum when there's only one peak in the temperature? And this has been a long-standing problem. I think it was finally settled by Dick Lindzen some years ago, but for a long time it was a mystery. So basically, these are just a couple of references to Venus. By the way, we do think that the thermal tides have a significant effect on the so-called superrotation, the main way that the atmosphere moves, because they do transport angular momentum effectively. But anyway, so the basic paradox for a long time for Earth and perhaps for Venus is, okay, so you get a phase lag, you're going to get a peak in pressure at 10 a.m., roughly 10 a.m. local time, and you can draw a picture that kind of explains that to you. But why are you getting it at 10 p.m.? Why are you getting it 12 hours later? So there's something missing from this diagram. And the short answer basically is that it's not really a sound bite, so I'm going to go through this in more detail in a moment. But the basic point is that the main forcing for these atmospheric tides is not the surface absorption of sunlight. The main forcing, and you can see this if you plot it in terms of forcing per unit mass, degrees per day, is all the way up in the ozone layer, which is, I said 40 to 60. It's even higher than that. It's maybe 30 to, well, anyway, somewhere around 50 kilometers. And so it gets complicated. If the main forcing is really in the ozone layer, then the question is, it's got to transmit its influence down to the surface. And it turns out that the semi-diurnal, the twice-a-day harmonic component of the forcing is preferentially transported. And so, as I mentioned, Dick Lindzen is the one who kind of worked this out some years ago and published this book, Atmospheric Tides. Okay, so now I'm going to go into the details of this theory. And it's important to do that because what I'm going to show you later is basically an extension of this theory, so I do have to set some of the background. I know this is a bit much in a talk, but I'll just take you through it. Well, first of all, if you want to look up this theory, you can read Chapman and Lindzen's book, but which is a great read, but for something that's a little more concise and uses the modern notation, I would highly recommend a book chapter written by Jeffrey Forbes in 1995. So to work out a linear theory of what's going on here with the atmospheric tides, there's sort of standard steps to do any kind of linear wave theory. First, you assume that there is some kind of perturbation going on. You assume small perturbations. That linearizes the problem. And that's a little too small to read, but basically you assume that they are wave-like. They have a certain wave number in the horizontal direction, and they have a certain periodicity in time. Okay, then you got these fluid dynamical equations based on conservation laws for mass, energy, and momentum. That is 5 equations and 5 unknowns. You condense them down to 1 equation and 1 unknown, and then at that point you've got a second order partial differential equation. At this point you've assumed wave-like variations in time and in horizontal dimensions, but you've still got latitude. I guess you assume wave-like perturbations in longitude and time, but you've still got variations in both latitude and altitude. So I'm calling latitude phi here and altitude x after it's been suitably normalized. For those of you right in the front row, maybe you can read that. Anyway, so you get one partial differential equation in this one perturbed variable. I've chosen basically the geopotential height, which is almost the same thing as the surface pressure, or the pressure. And then you go through standard procedure of separating the variables, which you can do because of the symmetry of the background states. That's something some of you might remember from things like quantum mechanics class, that's solving the Schrodinger equation. So you got one second order partial differential equation out of this linear theory. You go through the separation thing that introduces a separation constant, which I'm just going to call h. People sometimes call it equivalent depth. And you get 2 equations, 2 ordinary differential equations. One of them turns out to be exactly, well, not exactly, but very close to the equation that Laplace got in his famous book, Celestial Mechanics, when he was discussing the tides. So this is the so-called Laplace tidal equation, is basically what you'd solve if you were interested in ocean tides. And in that case, h, if you're just for the ocean tides, that's just the depth of the ocean. So it's an equivalent depth in this problem. There's another equation for the atmosphere, and that gives you the vertical structure of the waves. And this equation is, well, the algebra is very messy. I'm not showing you all that, but the equation at the end is really simple if you assume a simple enough basic state. I'm assuming here that you've got a very simple atmosphere to start off where you're running these perturbations. So in that case, with an isothermal atmosphere in the background, the vertical structure of the tides gets determined by this equation where the second derivative of the perturbation with respect to altitude is just some, well, isothermal atmosphere, that term would go away. So just some constant times the perturbation itself. So this kind of looks like a harmonic oscillator equation. So in the end, after all this messy algebra, which you can look up if you want to, you're getting a pretty simple equation for the vertical structure and a sort of a classic tide equation for the horizontal structure. So at that point, you need to solve the equations. What do you do to solve the equations? Well, that depends on whether you're dealing with the problem of normal modes, just what are the natural oscillation frequencies of the atmosphere, and to figure those out, you just say, well, we won't have any thermal forcing. There's this right-hand side. We'll just set this equal to 0. There'll be no thermal forcing, and then in that case, this equation, where the second derivative of the perturbation is some constant times the perturbation itself, and there's no forcing terms, that looks, now to me that looks, since I do kind of remember my quantum mechanics, this is just exactly like solving the Schrodinger equation for a free particle in a box. And so, but you know, you can think of a violin string or anything you like that's familiar. So there are, this is an eigenvalue eigenfunction equation. The eigenvalue are the different values of h. Remember, h is this equivalent depth. So the eigenvalues come out of solving this equation in the case of atmospheric modes. So in the case of atmospheric normal modes, no forcing, it turns out you just get, for an isothermal atmosphere at least, you get one value of H, so that's your eigenvalue, and you get, as it turns out, this constant here, mu squared, is positive. So second derivative is equal to some positive constant times the function itself. And for those of you who remember your differential equations, this means you don't have propagating waves, you have evanescent waves. If this constant were negative, then you'd have propagating waves bouncing back and forth. That's actually the case for the Schrodinger example. So you solve this equation for the values, the one value as it turns out of H, then you plug it into this equation, and that will give you certain, that's also an eigenvalue equation because locked up in this operator here, which is the Laplace tidal operator, you've got the frequency as well as the wave number. And so that's also an eigenvalue equation. Once you get the H eigenvalue from this one, you go back to this one, plug it in, and then the eigenvalues you're looking for are the frequencies, the normal mode frequencies. So you finally wind up getting, through that procedure, a set of normal mode frequencies, the natural vibration frequencies of the atmosphere. Now, what about the case of thermal forcing? That's the actual atmospheric tide problem because you do have this solar forcing going on in the ozone layer and elsewhere. So that's a different mathematical procedure. You take things the other way around because now you know what the frequency is. You know what the frequency of solar forcing is, right? It's once a day for the fundamental component. It's twice a day for the next harmonic. It's 3 times a day and so forth. So for each one, you pick the frequency. So now this equation, this Laplace tidal equation, that's the first equation you solve. The frequency is known, but now H comes in as an eigenvalue. So you solve the Laplace tidal equation for the eigenvalues. You get some associated eigenfunctions. Those are the natural tidal modes of the atmosphere that are being forced by the solar forcing. And somebody by the name of Hough was the first one to figure this out, H-O-U-G-H. So these are Hough functions. So with forcing, you solve this one first, get the Hough functions, then you go back to this one, the vertical structure equation, and say, okay, so I know what H is now. I figured that out from the previous equation. And this is now no longer an eigenvalue equation. It's just some differential equation with non-zero forcing. So you just integrate it numerically or however. And that gets you the tidal amplitudes. Okay, so that is the procedure. I hope I haven't dazed too many of you, but I think the main point is right up here at the top, that there are these 3 basic steps of assuming small perturbations, linearizing, reducing n equations and n unknowns to just one equation, and then going through the separation of variables. Very, very standard in wave dynamics from all kinds of fields of science. And so we're going to wind up with a linear theory. It's limited, of course, by the assumption of linearity, although that's not a bad assumption for the tides. And it is very, very robust. I guess that's really the main ultimate point I want to make here is this is a very standard procedure. We're not making any drastic assumptions. We're just going through linear wave theory. And so we're going to have some hopefully robust conclusions. So, okay, the question then is, okay, you've done this linear theory. Does this explain the observations of the atmospheric tides? Does it give you some reason to believe why is it that we're getting twice a day atmospheric tides out of solar forcing when obviously the solar forcing at the ground is, or anywhere else, is just once a day? And the short answer is yes. People tried to explain this for a long time based on something called a resonance theory. Very natural assumption to make if you've got this observation that you're forcing a system and the response is not doesn't seem to correspond that well with the forcing frequency, you can say, well, maybe there's just a resonance going on. Maybe there's a natural frequency of atmospheric variations that you would get by the procedure I just explained to you. Maybe that just happens to match this twice-a-day component of the solar forcing. And so lots of people, beginning with Kelvin and Rayleigh, came up with this theory. It turns out that the resonance A is very sensitive to what the assumed background state is. If you assume an isothermal atmosphere going up in altitude, you don't get any resonance that will explain the observation. Of course, the real atmosphere is not isothermal. As people started exploring it, they're saying, well, maybe there's this or that going on. It turns out that for a while, going up through the mid-20th century, people thought they had convinced themselves that the resonance theory was correct. It's a good example of, we all believe this theory, but then it turned out to be wrong. That's because up through the 1950s, the idea that there was a temperature peak at the mesa pause at about 50 kilometers altitude was becoming obvious that there was a temperature peak, and if the temperature peak was big enough, it actually would have caused this resonance effect. But it turns out when better data came in, it wasn't big enough, and so the whole theory just kind of collapsed. So, second try, Lindzen, building on other people before him. Like I say, it's not a simple soundbite, but it is a robust theory. I want to really make that point. This just comes out of the basic linear wave forcing considerations. And the key point here is that ozone heating is the primary driver. I'm actually going to take the liberty of quoting myself here. One of the earlier papers that I published with Dick makes the point that the response, the tidal response that you see at the surface in terms of the surface pressure scales as it scales inversely with the density of the atmospheric density at the forcing level. Now, the paper goes through this in some more detail than I could write down here, but basic point is that forcing in the ozone layer, where the density, of course, is much smaller than at the surface, actually gives you the main response at the surface. So the tides are basically forced in the ozone layer, believe it or not. And now we get into this question of wave propagation, going through this linear business and looking at the vertical structure equation. Of course, the once-a-day harmonic of forcing will dominate. It's about, I think it's more than twice the next harmonic, the twice-a-day semi-diurnal, but it propagates much more effectively. So you go through the details of this procedure I showed you in the last slide. What you find out is that the once-a-day response is set up in the ozone layer, and in fact, by the way, it is very clearly observed in the upper atmosphere, and something the upper atmospheric observations over the last few years have told us. You can really see it in the upper atmosphere, but it's vertically trapped. It has an imaginary wavelength, basically, so that means it just has an E-folding depth of less than 5 kilometers, so it's just trapped where it's forced, and it's suppressed at the surface. The next harmonic up, actually the next harmonic up for the once-a-day forcing has problems too, destructive interference, but the twice-a-day, the higher harmonic of solar forcing once every 12 hours will, as the theory will show you when you go through the details, it will propagate very efficiently to the surface. So that's basically the answer to why we're seeing this twice-a-day surface pressure peak. Okay, so what does this have to do with climate modeling? A few years ago, it occurred to me that these climate models ought to be, because they are weather prediction models after all, they ought to be simulating these atmospheric tides. Now, it turns out that other people who were in the weather prediction business knew that already, and in fact, one of them told me that, we use this routinely as a way of checking out our model behavior, but I didn't know that, and other people in the climate modeling business apparently didn't know that. So I decided I was going to look at all of the models in our database that provided high frequency data. This is CMIP Phase 5, the latest and greatest version of CMIP. Turns out there's 26 models that provide high frequency data. They're all listed here, way too small for you to read. But the interesting thing about these models is that some of them include the ozone layer and some of them don't. This is basically telling you how far up in the atmosphere are these models. Here's the troposphere where we live. This is about 10 kilometers altitude where the stratosphere starts, 50. You get the mesosphere, 80 and above you get the thermosphere. Some of these models, like this one in particular, this is called, it's a wonderful name, WACCM, the Whole Atmosphere Community Climate Model. This one is a close relative of WACCM, basically the same model, but WACCM goes all the way up through the thermosphere. Latest version goes even higher, probably goes to the second floor of this building, but anyway. This is kind of the standard model. CCSM4, it's, I think, the most widely used climate model in the United States. And that just goes most of the way up the stratosphere, but it misses most of this level of ozone forcing, which is in between the stratosphere and the mesosphere. So I looked at these models, and I'm going to show you a little synopsis of what I got, although I'm running out of time here. So taking these two particular climate models, WACCM and CCSM, very close relative, and just running through a Fourier analysis and saying, what is the amplitude of surface pressure perturbations? Well, here's the observations. And this scale goes from 0 up to, well, the yellow is about 120 pascals. Red is 200. Observed, this is the low top model. This is the high top model. So this is for the once a day harmonic, the one that's not actually dominant in the observations. And it's quite striking here that as far as the once a day harmonic, which is not forced by the ozone layer because the ozone forcing part just doesn't get through, what's left is much closer to the surface, things like water vapor absorption near the surface and, of course, surface absorption itself. The two versions of this model, whether they get a high top or a low top, just doesn't make much difference to the once a day harmonic. But what about that twice a day harmonic? Okay, observations show that it dominates. This is a bit bigger than that. And low top model, high top model. So the model with the more complete upper atmosphere, the WACCM model, gets a much bigger amplitude than the low top model, which is what we're expecting because most of this is forced in the ozone layer. However, it's bigger than the observations themselves. That's a little mysterious. I think the observations are pretty reliable, so maybe there's something funny going on with this model. On the other hand, this model hardly includes the forcing, and yet it's getting the right answer. So this is where we come into maybe this is a case of models getting the right answer for the wrong reasons. And in fact, if you read the papers that we published, we found that all of the models in the intercomparison project overestimate this twice a day harmonic, even though many of them omit most of what's supposed to force it. So it's getting rather complicated here. And apparently we have some compensating errors going on. So I do want to say some word about that. One thing that could be going on is all models of the atmosphere have a top somewhere. You can't make well, at least all numerical models, you can't do a numerical integration over an infinite domain. Theoretically you can do it, but you got to put a limit somewhere. So they have a top somewhere, and some time ago, Dick Lindzen, long time ago actually, published a paper where he pointed out that if the atmosphere has an artificial top, then it's no longer the case that you get this one equivalent depth like you did in the homogeneous problem with an unbounded atmosphere. You get an infinite number of equivalent depths for which the vertical structure equation has some solution. And these constitute what people call Rossby-Horowitz waves. That's not very important, but in an infinite atmosphere, you only get one value of H. Bounded models will have lots and lots of modes associated with these spurious values of your eigenvalues. So physically what's going on is that if you put a top on the atmosphere, it's possible that you're going to get wave reflection in standing waves, which of course is non-physical. The real atmosphere doesn't have a top. So what do we do about this? What I did, which I think goes one better to what Lindzen did some time ago, I just solved the homogeneous problem in the case of a general top on the model atmosphere. Now, unfortunately, solutions here kind of dropped some symbols off my slide. PowerPoint didn't like them. But what I'm basically showing here is eigenvalues on the horizontal axis and the level of the model top on the vertical axis. So this is basically raising the model top. If the model has a top, say, at the 200 millibar pressure level, then you've got these lines which represent the normal modes that come out of the calculation. And so if your top is at 200 millibars, that says you're going to get a resonant frequency standing wave at a certain eigenvalue, which is totally artificial. I mean, it's not, there is no real top of the atmosphere at 200 millibars or 10 millibars or anywhere higher. Modern climate models, by the way, all go up to 10 millibars at least, or even higher levels. So they're all up here somewhere. But the spurious modes are always there. And the question is, are you forcing the climate model at a frequency that coincides with the spurious mode? For instance, if your climate model has a top at 10 millibars, it's going to have normal modes at this eigenvalue, and then at this eigenvalue. I'm looking at where the dotted black line intersects these violet lines. And oh, by the way, we're also forcing them at certain eigenvalues that are determined by the solar forcing. And so basically, if you have a three-way intersection here, where the model has a top which happens to have a spurious normal mode at a certain eigenvalue, and that happens to be an eigenvalue that's associated with the forcing, then you're going to get a fake resonance. So that's maybe why the models can get the wrong answer, the right answer for the wrong reasons. Now, I'm in the middle of this calculation, so don't take it literally, even if you could see all these symbols. But that's kind of where I am right at this moment. And by the way, we're very interested in collaborating with people on this. Dick is retired. I have other things to do. So if there are people out there who like old-fashioned linear wave theory, I'd love to hear from you. Okay, let me just make a switch to a related subject for the end here. I want to talk a little about the diurnal cycle of precipitation. As I was saying, this is an opportunistic move on my part because I realized one day, well, I can take these scripts that I've been using to analyze what the climate models are doing about once a day, twice a day, other harmonics of surface pressure. I can apply that to any of the 23 different output fields that CMIP provides at this frequency. So why not start taking a look at others beginning with precipitation? So that's what I did. Certainly nothing new. It's been done in the past. But here's what I'm getting. What I'm plotting here is the phase of the diurnal harmonic, the once a day, 24-hour harmonic. And I'm not taking this from a model. I have other plots for the models that I don't have time to show you, but this is from that OBS for MIPS database that I mentioned, and I used that to pull off data from the Tropical Rainfall Measuring Mission, which, by the way, has just been superseded by an even greater mission called GPM, Global Precipitation Measurement, but TRMM already gives us stuff at 3-hourly frequency, so perfectly suited for comparing with the model output. And this is the phase, just a map of the phase for January, a map of the phase for July, and by phase, I mean the local time of day when the precipitation hits a maximum. So here's the scale. It's a wraparound scale, by the way, so 0 and 24 are both red. So is the maximum at midnight, or is the maximum at, say, 10 in the morning, or maybe late in the afternoon? Anyway, it pops right out things that people have noticed in previous years. The main thing, quoting a paper by Igbo Dai, is that over land areas in the summertime, January, summertime, southern hemisphere, you're getting these violet colors. That means that there is a maximum rainfall kind of late in the afternoon, getting into the evening hours. Whereas for ocean areas, a little more confusing over ocean because the cycle itself is weaker, so it's harder to get the phase out. But you're getting kind of yellow-green colors, which means morning time peaks. A lot of interesting little features pop out of this data. One thing you can see here around Indonesia is a very sharp contrast between what's going on in the ocean with this early morning peak and land areas with late afternoon peak. If you can't do this, but if you really go up and stare at the details there, you start to see things like propagation of systems. Well, you can see it best here in the middle of the North American continent. This is something that was first noticed way back in 1989 from regional data, that you see these color stripes basically mean that what's happening in the summertime, this is July, in North America, as you start forming these mesoscale complexes of convection that pop off in the Rockies, and then they propagate across the plains and finally wind up peaking rainfall. See these tiny bits of yellow color peaking, or I guess, yeah, yellow color. So you finally you get peak rainfall in, say, Illinois in the early morning hours. And so it's this really neat wave propagation thing. So there are lots of things that the models ought to be telling us. Do they, in fact, tell us that? That gets back into the core mission of the group I belong to, the PCMDI. We're supposed to be inventing clever diagnostics to try to summarize what the models are doing. So how do we summarize how models are behaving? If this is the observation, well, we could have 2 plots for every model, and there's 26 models. Well, that would drive me crazy. So one thing, well, you can integrate over areas, but it's very obvious that in this case you should integrate the land and ocean areas separately. And my favorite technique that I'm coming up with is one that's really an old technique. This is a diagram again from Chapman and Linds's book, and it actually refers back to something else you can't read here, but this goes back to somebody's publication in 1932. It's called the harmonic dial approach. Basically, you just draw a clock face, and you have the dial of a clock face point to where is the maximum, and then the length of the arm that's pointing up to the hour is the amplitude. And so you get both amplitude and phase. And just treat the amplitude and phase as a 2D vector and average the vectors. And you do tend to get something coherent here. So this is what I'm going to end on. Another thing that I'm in the middle of, trying to summarize how the models are behaving for the diurnal cycle of precipitation. I've got a set of averages over land for the 24-hour harmonic and the 12-hour harmonic. I've got another set of averages separately for ocean. These are the length scales that give you the amplitude. They are different because the oceans have a much weaker amplitude. And the observations, again, from TRIM are these black lines. So here's the observations are telling you that the 24-hour harmonic, for instance, from TRIM is, what is it, maybe about 1.5 millimeter per day amplitude, and the phase is going out a little after 1800 hours. So on average over land, late afternoon, early evening peaks in precipitation. So that's the observation where I'm trying to hold this steady. And then everything else is a model. And look where the models are. The models are way too early. And they're way too early over ocean. And this is kind of the elephant in the room, something that people have been noticing for a long time. This quantifies it. And so here again, a case of models giving you right answer, but maybe for the wrong reasons. If you add up their precipitation over a period of 1 or more days, they're not bad. You get a map of precipitation, looks realistic, but it's happening too early in the day. So there's something the models are doing that's wrong. They're doing it the wrong way. Is this important or not? I think it's unfair to say, well, if the models make any mistake, we'll throw them out and forget about them. I mean, that's the road to randomness, basically. This is not particle physics. You can't expect. Well, go into that. Okay. So this is a model problem. It's certainly been recognized over the years by many people. This is a way of quantifying it. Maybe it's a way of making the models better. And that is basically the purpose of the PCMDI. So hopefully I'm contributing something here. So as I said, I'm going to leave you hanging. This is it. I'm leaving you hanging. And thanks very much for coming and listening.
Thank you for a great talk.
Oh, you're welcome. And
take some questions.
Before I forget, yeah, this is yours.
Excellent. So please wait for me to bring you the microphone.
I'm KRS Murthy. I mentioned to you offline that I built the first ozone measuring ultraviolet spectrophotometer, which went on the first space shuttle, measuring the ozone concentration in the upper atmosphere. Has that data been fed back to your analysis in terms of ozone concentration? How does it affect the atmosphere and so on? And if required, I can go back to NASA from the first space shuttle.
Well, I have to ask you a question before I can answer your question. What altitude were you looking at with your instrument?
This was a space shuttle which it was the whole range of whatever it was going into.
Yeah, so presumably it's looking at the horizon and scanning down somewhere. So was it really seeing down to the peak of the forcing at 50 kilometers? Okay.
Yeah, recovered. And I can go back to the data, which I don't have handy now. Want to see how that would affect your models and so on.
No, I haven't used it, but I'd love to hear from it. I should probably give you my email, because
I can.
There's no more blackboards. I can't write it.
You can just tell me. I'll remember one.
Yeah, right. Okay. So I'll tell everyone.
Yeah.
Last name is Covey, C-O-V-E-Y. If you type Covey1, the digit 1, at llnl.gov. That's my email. I'm welcome further discussion by email.
Thank you. Excellent. Thanks. Other questions?
So given how wildly inaccurate these precipitation values of the models are based on that last slide, I'm wondering, do we have any climate models that can predict the California drought's future? Or is it just like the noise is so high that the signal's lost?
Well, offhand, I don't think this problem that I pointed out is critical to the drought issue, because I don't think it matters what time of day the rain falls. If the models can make it fall sometime during the day, that's probably good enough for the drought issue. The real foible of the models, I don't even foible, but the challenge for the models is predicting the development of these high pressure ridges that steer the storm tracks. Now the storm tracks themselves are something that's pretty well understood through both linear theory and numerical modeling. But the blocking highs that come up, that's very nonlinear, and the models aren't so good at that. They do other things fairly. I mean, they do basic thermodynamics well. And so one of the things that we're pretty confident about, which is very influential on hydrology, is just Clausius-Clapeyron, that warmer air can hold more water, vapor. And so we expect in a warmer world the whole hydrological society, the whole hydrologic cycle speeds up, which means that areas that start off dry get drier. Areas that start off wetter than average get wetter. Well, unfortunately for California, we are on the dry side of the average. And so if I had to bet, just based on that, I would bet that we're likelier to have greater risk of drought in a warmer world. And then the models will, of course, elaborate on that, and people publish papers. I think I gave you one reference from colleagues of mine at Livermore, and that will lead you to others. The models are saying we're probably, Western United States at least, is likely to get drier. So, I think making a statement like that is perhaps helpful, but it's, people who build dams and things, they want more precise statements. I don't think the models are capable of more precise statements at the moment.
Other questions? You answered them all? Oh, one more.
If you look at the wettest areas of the Earth, most precipitation
Yeah.
that happens
Yeah.
on the other end of it, does it at least correlate the extremes, if not in between? Driest, like the Sahara Desert, all the way up to the Himalayas.
You mean, do the models simulate that
at
accurately?
least does it show that those places are the wettest and the driest, at least if not in between?
You're talking about do the models?
Yeah.
Yeah, okay. Yeah, they have a good correlation.
If you can take the high end and the low end.
It's more than a good correlation. I mean, when I look at a modern model simulating the average precipitation, never mind what time of day it happens,
Yeah.
but just, what is the average July precipitation in a model?
Yeah.
What is it in observations?
Yeah.
I can't even tell the difference. Now, an
I'm not
expert could
talking
tell the
average,
difference, but it's a very tight correlation.
Average is a bad way to do statistics.
What?
The average is a bad way to do statistics.
No, well, I'm
It's
talking about
extremes.
correlation.
Extremes.
Yeah, right. So the correlation, I think it's at least 75%.
Okay.
So they're doing something right.
Okay.
Yeah.
Excellent. Let's thank our speaker one more time.
Yeah.
Thank you again.
Thank you. And thank you from the SETI Talks series. I wanted to give you this SETI Talks mug.
Oh, lovely. Thank you.
Enjoy. Great, and I hope to see many of you here next week.